Hello everyone and welcome to the afternoon session. Just a reminder to fill out the post-conference questionnaire, ideally by the end of today or certainly at lunch tomorrow, so I can announce the results afterwards. So this afternoon we'll have talks about dwarf galaxies and the tidal stability, which relates partly to what Hongxi was talking about, the tidal radii of galaxies. Be some talks related to this. So I'll hand over to Jonathan Freundlich to start the afternoon talks.
Hello, so I'm Jonathan Freundlich, and so I'm faculty at the Observatoire astronomique de Strasbourg. And today I'm going to talk about Coma cluster ultra-diffuse galaxies as a testing ground for MOND, which is some work that we've been doing with Benoit, Pierre-Antoine Loria, Michel, Oliver, Rodrigo Ibata, and also with Shrikant, who's the next speaker. So there is a lot of background that I probably don't need to explain. So let me just remind you about the external field effects. So the external field effect is a peculiarity of MOND as a modified gravity theory. Namely the fact that the nonlinearity of the MOND gravitational field induces a violation of the strong equivalent principle of general relativity. So in general relativity, you can isolate a system that is embedded in an external field, and its internal dynamics do not depend on the external field. And so in MOND, this is a priori not the case, in the sense that the internal dynamics of the system should depend on the external field in which it is embedded. And so if you take the same dwarf galaxy isolated, it should have velocity dispersion that is predicted by the MOND in isolation formulae. And while if you take the same system and you embed it into an external field, you end up in the strong acceleration regime, and so which means that you expect this system to behave as a Newtonian system, and hence the velocity dispersion to decrease. So in this talk, I'm going to look at specific galaxies in the Coma cluster as a testing ground to try to see if we can see an effect of this external field or this violation of the strong equivalence principle, namely ultra-diffuse galaxies. So these galaxies are dwarf galaxies that have stellar masses, or generally that have galaxies that have stellar masses of dwarf galaxies, but sizes comparable to the size of the Milky Way. So they are extremely low surface brightness objects, and so this means that they have singularly low internal accelerations of only a few percent of A0, while if we look at such galaxies in the Coma cluster, they are in a strong external field, the field of the cluster. So what we did here is that we looked at ultra-diffuse galaxies in the Coma cluster that had a priori reliable stellar velocity dispersion measurements. So at the time of our study, there were 11 such galaxies, so namely these two galaxies that have been studied by von Dockum and his team, including DF44 that has been relatively popular, and an additional 9 galaxies for which the stellar velocity dispersions were measured by Igor Shinigarian. So this is an image of the Coma cluster taken by the Dragonfly telephoto array. And just to give an idea, this is how these ultra-diffuse galaxies look like. So this is DF44, DFX1, and different types, like the morphology of these 11 galaxies with stellar velocity dispersion measurements. So the first thing that we looked at was the radial acceleration relation. And so I think that different people have introduced this at different occasions. So I think we've extensively talked about it, namely the relation between the observed acceleration field derived from the kinematics, so which is here we used this formula from Wolf et al. 2010, depending on the effective velocity dispersion, so which is the mass-weighted velocity dispersion we can observe. And this expressed in terms of the baryonic acceleration, which is the gravitational acceleration that you expect given the observed baryons of these objects. So for this, we used models that were derived in the article by Igor Shilingarian in particular. So we have Cerseic fits to these galaxies. What we do is that we deproject these Cerseic fits using a formula by Limanetto et al. 1999, which is an approximate expression to deproject such a profile. And we get this baryonic acceleration, and this is the resulting radial acceleration relation together with the spirals from Magdoff et al. 2016, dwarf spheroidal galaxies by Lely 2017, and here these additional points here. And so, as you can see, these points seem to lie on the relation that you expect, that you can see here, and which correspond to the isolated MOND prediction here. And this is actually quite unexpected in the sense that these galaxies do lie in a strong external field. And so we would have expected that instead of, within the framework of MOND, we would expect these points to be to fall down from this relation to come towards the Newtonian prediction if the external field effect is strong. And so I think that on Tuesday, Edwin Valentine also presented some similar results for the Fornax dwarf galaxies, so results by Sarah Eftekari, I think, which also show that the Fornax dwarf do also seem to fall on this relation here, despite being in a strong external field. So this was an indication already that there may be something at least unexpected or off with the external field effect in these galaxies. And so we tried to look a little bit more precisely into this issue by doing different models, predictions within the MOND framework for the velocity dispersion profiles of these ultra-diffuse galaxies. So what we do is that we take the observed stellar distributions of these objects, from which we can be fitted by Cerseic profiles. We deproject these Cerseic profiles to get the 3D, the corresponding 3D distribution. We assume uniform mass-to-light ratios, so which are of the order of 1.3 we assume for DF44 and DFX1. And then we calculate the line-of-sight velocity dispersion from Jeans equilibrium. And so by doing that, we are having a prediction for the MOND model in isolation without any free parameter, just from the observed baryons. And so here are two examples where you have the graded data points in the shaded area here corresponds to the effective velocity dispersion, and the dotted points are the Newtonian predictions, just assuming the baryonic distribution, while these plain lines correspond to the isolated MOND predictions. And so, as you can see, it does give the right order of magnitude, and this is the case for all the galaxies. And also, for example, if you add some degree of radial anisotropy, so these are different anisotropy parameters, so beta was plus 0.5, which would be a radial anisotropy, and minus 0.5, which would be a tangential anisotropy, it also seemed to reproduce relatively well or better the observed trends, for example, here in this galaxy, for which we have multiple measurements at different radii. And so, even though you can argue that here, for example, the red line does not fully correspond to the observed data, I would like to recall that this is without any free parameters, so which means that there is absolutely no reason to even get the right order of magnitude here, per se. And so it does seem that the MOND model in isolation works relatively well and fairly very well to describe these velocity dispersion curves. But then this is in isolation, while we are in a cluster environment, and so we move towards trying to model the external field effect. So in this effect, we need to model the mass of the cluster in which these galaxies are. And so to do that, we relied on an article by Sanders 2003 and also Weiprych 2001, so which basically derive the mass profile of the Coma cluster from hydrostatic equilibrium of hot X-ray emitting gas. And so I won't go into the details, but basically you can observe the distribution of this hot gas. You can measure its temperature, and from this you can get the dynamical mass of the cluster, first in a Newtonian setting, and you can also do the same thing in a Mondian setting to get what should be the dynamical mass, which is this plain line here. The red curve here is the gas mass derived just from that can be seen here. So after that, we also needed to properly account for the external field effect. And so there is a formula in Freundlich and McGough 2012, but which is a 1D formula, in the sense that that means that it's in the case where both the external field and the internal field are aligned. So which means that this formula is actually overestimating the external field in different situations. And so we derived a different formula that corresponds to the average field we would expect in a sphere that is embedded in a constant external field in the MOND formalism. And so these are the formula that we got, and we tested this formula in Poisson numerical solver. And quite surprisingly, we found that that was giving predictions that were extremely good to reproduce the velocity, the acceleration field, as you can see in this example. So here, what we're doing is that we're putting a Plummer sphere around point mass that has the mass of the Coma cluster, and we look at the acceleration field in this Poisson numerical solver, in the MOND formalism, at different distance, and we find an excellent agreement, as you can see here. And if we look at this plot, I think that this is quite interesting, and it also shows how this formula overestimates the external field, in the sense that what you have here, that this is the internal field divided by the Newtonian equivalent. So in log, so when it's 0, it's Newtonian, so that's what you expect in a very strong external field. When it's in isolated, you expect this relation, which is the red line, vertical line here. It's not at 1. And this is as a function of the strength of the external field with respect to the internal Newtonian field. And so you can see that when the external field increases, you fall down from the isolated MOND regime towards the Newtonian regime. The dashed line corresponds to the Freundlich and McGough equation, so it's relatively early, while this formula corresponds to the plain line here, and the red points are the tests that we did with this Poisson solver. And as you can see, it fits relatively well, at least much better than this initial equation, one-dimensional equations. And so, given this success, we took this relation to estimate what should be the velocity dispersions in these UDGs, taking into account the external field effect. Again, all of this in the MOND formalism. So this is what we get. We do the same steps as before, plus a MOND mass model for the Coma cluster, this new analytical formula for the external field effect. And what you see here is for isotropic case and also the radial case at different distances. So at a distance of 10 megaparsec, 5 megaparsec. And here d mean, it's actually the average distance at which we expect the UDG to be, because we only see a projected distance for the UDGs, and so we need to try to get some estimate of the real distance at which it is, in the sense that the real distance is necessarily higher than the projected distance. So this is the average distance at which we estimate the UDG to be, given some distribution, radial distributions of the UDGs in the cluster. And what you can see is that this estimate here leads to a very low velocity dispersion, so which means that when we do this for all the galaxies, there is a tension between the observed velocity dispersion measurements and the expectations with external field effect here. Basically, we do not see any evidence for a violation of the strong equivalent principle from these observations, or we do not see any sign of the external field effect in these galaxies. So then we try to understand what could be the possible explanations for this in the framework of MOND. And so one first hypothesis is that maybe these UDGs are much further away than we see them given their projected distance. So I think that this is actually quite unlikely, because if we look at the distribution of projected distance, you see in black, this is for all observed UDGs in the Coma cluster, and in blue, dotted blue, would be the expected distribution if all these UDGs were further than 10 megaparsec from the cluster. Because as you could see in the previous plot, to be able to neglect the EFL, you really need these UDGs to be very far away from the cluster. Then there are other possibilities that we are looking at, which is also that these UDGs could have only recently arrived in the cluster. And so this is notably understandable in the context of MOND, in the sense that we expect tides to be stronger for these galaxies when they are in the cluster environment, precisely because the external field effect decreases the velocity dispersion, and so they are more prone to be disrupted. So maybe the UDGs that we observed are all on their first inform. And so we do not exclude this possibility. And another possibility is that these UDGs would be tidally disrupted or tidally heated here, which may be possible given that they have relatively elongated morphology and that their tidal susceptibility is relatively high. And so here we calculated the tidal susceptibility in the same way that Hongshen proposed. And as you can see, the tidal susceptibility, which is the ratio between the tidal radius and the half-life radius, is for these UDGs with EFE between 0.5 and 1, so which means we do expect them to be affected by tides. And so these points are points that Shrikant are going to talk a bit more using numerical simulations just after me. And I want to mention some other possibilities that we explored about these explanations. So one possibility is that these objects have higher stellar masses than we assumed, in the sense that here we assumed stellar to m over L ratios that are of the order of 1, using relatively standard procedures, but maybe these galaxies are not standard. And so we looked at what would be the best fit mass-to-light ratio that we would need to explain the observed velocity dispersion, and we found that it's around 10, so quite significant. But that with stellar m over L ratio of 4, we could get some relatively good fit. But it does, so that's a possibility, but it would mean significant increase in the mass-to-light ratio, although this could also act in concert with, for example, the effects of tidal heating. Finally, other possibilities are modified inertia. So Moti did talk about it, so which could provide a framework where you do not have an external field effect, or where the external field effect would depend on a galaxy individual history. We explored the possibility that there could be an additional degree of freedom, namely in the context of MOND, you assume that the acceleration scale A0 could depend on the depth of the potential, and so that's from Zhao and Famae. So where you see that in clusters, the A0 could be as high as around 10, and so taking into account the gas distribution of the halo, we computed what would be the expected effect on the UDGs, and as you can see, it does provide relatively good fit again, especially with radial anisotropy. And finally, another possibility that could help solve this tension is, for example, maybe in the context of models such as those proposed by Konstantinos Skordis, or Skordis and Zlotnik, here is that maybe there may be ways to account both for the missing mass in clusters and at the same time for the lack of external field effects that we see in these clusters. And so, to conclude, I presented the work that we did on the Coma cluster ultra-diffuse galaxies as a testing ground for MOND. And so what we show is that these UDGs lie on the same radial acceleration relation as spirals in the field, that their velocity dispersion is in agreement with isolated MOND predictions, but in tension with the MOND models, including the external field effect. So we looked at different explanations for this tension, so including recent infall, tidal interactions, higher M over L ratios, or even cluster baryonic dark matter or modified inertia. I think that there still is a question as to why does isolated MOND work so well, in the sense that you can say that maybe the M over L ratios are higher, or tides bring the velocity dispersion higher, but then why would it be precisely at the level of the isolated MOND prediction? And so it may seem a bit like a conspiracy, but of course it may also indicate the need for further theoretical development, and I think that this kind of discrepancy may guide the type of developments that could be necessary to reconcile MOND in this context. Thank you.
Excellent talk. So we'll take like a few questions. Yes, quick one.
Just wondering, what is the ratio of dynamical times internal to sort of external?
Yes, so I did a very rough measure. I think I quoted here. That was the time in the cluster is about 3 to 6 times that of inside the UDG.
Internal.
The internal time.
But internally, you mean like one coursing or half a coursing?
Here it's basically the orbital time at the half-light radius.
Well, one possibility is that if they are falling from outside, you're basically seeing they do not have time to adjust to the new standard field. You're seeing the velocity dispersion that corresponds to what they were from.
Yes. Maybe I was a bit fast in this, but this is precisely what I wanted to convey here in this option, that they may still bear the velocity dispersion that they had long ago when they were just before coming into the cluster environment.
So someone we haven't heard much from before. Okay.
I noticed on your map of the locations on the sky that all these objects are along an arc. Do you have a comment about that?
No, I don't have a comment. I think this is just an observational bias, in the sense that these are just the objects that have been observed, for which we have stellar velocity dispersion measurement. If you look at all the UDGs in the Coma cluster, there are much more than this, like hundreds of them, and they are all over.
The M over ratios in which photometric band are they?
What?
The M over L, in which photometric band?
Oh, I'm not exactly sure. I think it's I band maybe, but I'm not entirely. I mean, I think the M over L ratio were obtained. So in this article by Igor Shilingarian, by fitting different bands, but I'm not exactly. I don't remember exactly.
Okay. No, because I mean, 4, if it's B band or V band, is completely reasonable, and actually 1 would be too small. But yeah.
No, I think
I need to know what the L refers to.
Yeah, that is true. What color band it is.
Yeah.
And a related comment, it would be very interesting to have colors as well, if you have multiple bands, because then, you can have a better idea of the stellar populations.
Sorry, did you say that the M/L was already obtained based on the color?
Yes.
The figure of 1 is based on the color.
So the first figure, this one?
No, the assumed M/L of 1 is
Yes.
based on the color.
Yes.
Okay. Right. Yeah, thank you.
Concerning these dwarf galaxies, I suspect most of the stars are binaries or even higher multiples. Then these internal motions may have contributed to the velocity dispersion. Have you taken that into account in your model?
That's an option we did not discuss. Indeed.
Oh, actually, that could be very important. I mean, it seems that for dwarf galaxies, actually most of them could be binary, more than half. And then some of them will be higher order multiples, triples, even quadruples. And then internal motions contribute to the velocity dispersion. So the observed velocity dispersion is boosted velocity dispersion given the gravitational field.
Sorry, what sort of velocity dispersion do you have? 20, 30 kilometers a second?
Yes. Here you can see.
Yeah.
30, 40.
Okay, this is good idea. And any more final quick question from anyone? All right, if not, we'll get on to Srikanth's talk.